All right, so what we'll do now is we'll quickly review the iris logistic regression solution, the thing that I've uploaded. So we talked about this exercise. We took some time to solve this exercise, and this is the data set that we have here. Sepal length, sepal width, petal width, and we are trying to predict the variety. As I told you, this is the kind of a multi-class classification that we are trying to do. So what is the difference between binary and multi-class? Binary is where we are trying to predict between two classes. So we have either yes or no. Okay, either you're diabetic or you're not diabetic. Either the cancer is malignant or the cancer is benign. So you have only one out of two answers that are possible. That is what we refer to as binary classification. Multi-class classification is where we have multiple possible answers that could come. So that is the exercise that we had here. And we are going about it. We are doing some basic data analysis. You can see the info method. We do not have any missing values. There are 150 rows of data. There are 5 columns. We already talked about the iris dataset. It's a very old dataset. It dates back to 1930s, uh, and a very, very popular academic dataset that we have here. Next up, we are looking at the pair plot, something that we talked about in uh, the previous discussions. And you can clearly see from the pair plot that we have a very strong separation between the classes. So when I do the pair plot, we are able to see that sepal length, sepal width, petal width, the four features that we have, the classes, the different varieties of flowers that we have, like Iris setosa, Iris versicolor, Iris virginica, we are able to see a very strong separation between the classes. So you can see, especially with respect to the petal length and the petal width columns, specifically with respect to the petal length and petal width columns, we can see that the classes are very well separated. The varieties of flowers are very well separated. That means if, in other words, if we know the petal length, we can very accurately predict the variety of flower. So if we have a higher petal length, we know that it's a virginica. And if we have a lower petal length, we know it's a setosa. If we have a higher petal width, we know it's a virginica. And if we have a lower petal width, it will be a setosa. So by looking at the petal length and petal width, we can very easily separate the classes of flowers. The same thing we can do for sepal length also. Okay, so but if you see the sepal width is not a great feature, that means the classes are overlapping. That means if I just know the value of the sepal width, that is not enough for me to be very certain as to what type of flower it is. We are not able to see a very strong separation between the classes. So the pair plot is a wonderful way that tells us in a data set, are the classes well separated? If the classes are well separated, then generally my algorithms will do very well to separate the classes. We will have a higher accuracy in the classification model. But like we saw in the diabetes exercise in the previous discussion, that the classes were not that well separated, and which is why in the diabetes data set, we only got around 70% or 80% accuracy. Whereas in the cancer one, we touched close to 94, 95. And same in iris also, we will touch close to 94, 95% accuracy. A slightly more numerical way to identify the best features is using something called feature importance. So this is based on some other mathematical techniques like entropy and information gain, which I do not want to get into. But the concept part we talked about in the previous discussion, where you can use feature importance and you can see that uh, the relative importance values of the features. So one is the visual approach, and the second is the mathematical, the quantitative approach, which you can use to identify that which are the best features. And now once you know this, once you are able to see that, okay, steeple width is not a very good quality feature, what you can do is you can now in the next iteration, you can drop the steeple width and rebuild the model. Okay, so the next iteration, what you can do, you can drop the sepal width column and you can rebuild the model without the sepal width column. And this is the experimentation part that we do in machine learning. We constantly try out different things. We try building different models, and we try to build the best model. So this is what we will do in the next iteration. Anyways, most of you are able to do this. So we are using a pipeline. I'm sticking to a basic logistic regression model, and I'm getting close to 96.67% accuracy. The answers can be different, and the reason why the answers are different is because some of you would have taken a different train test split. Your ratios would have been different. So if you're using a different training data, a different testing data, you will get a different answer. And we also discussed that it's not right to trust this single accuracy number, because the testing data set could be biased. It could be that the testing data is too easy or the testing data is too hard. So it is not right to rely on a single accuracy metric. Rather, we calculate multiple accuracies and calculate an average cross-validation accuracy. We talked about that. Now coming to the predict proba, we will have three probability values that will come out of it. Why? Because there are three classes. So first part is you build a model, and the second part is you use that model, you use the trained model to do predictions on the testing data. So we will use predict proba, and this time predict proba will return three class probability values to us. And what are the different numbers we are seeing right now? So the first one that you see is the probability of setosa. Let me write it down. This is setosa S. The second one is the probability of versicolor, VE, and the third one is the probability of virginica, VI. So what Python will by default do is it will typically sort your data in ascending order, and it will typically display your data in ascending order. So S will come first, then VE will come, E comes before I, and then VIR will come because I comes after I. So Virginica will come at the end. So this is the way Python will sort your data internally. Because remember, as per my data set, as per whatever data set I gave, I only gave the actual values here, setosa, versicolor, virginica. So this is the way how it's sorting. And internally, in all the computations and all that it does, it will internally go and list out your data in this alphabetical order. Even later on, when we see the confusion matrix, there also you will see that the data will be listed out in a alphabetical order. Okay, so that's an important thing to keep in mind. So very clearly, the probability of setosa is 93.58%. What is this E minus 0.1? E minus 0.1 stands for exponential. It means 10 to the power minus 1. E minus 0.1 means 10 to the power minus 1. That is the meaning of E minus 0.1. Okay. So what is E minus 0.1? E minus 0.1 means 10 to the power minus 1. So that's the inference we can get out of it. So E minus 0.1 means 10 to the power minus 1. That's the inference we can get out of it overall. So very clearly we can say that. So very clearly we can say that. Okay, this is 90.93. 10 to the power minus 1 corresponds to 0.93, which means there is a 93% chance that this is setosa. There is a 64% chance that this is versicolor. Sorry, there's a 6.4% chance it is versicolor, and there's a very, very small probability is virginica. So whichever the probabilities are high, wherever the probabilities are high, the model will predict that. The model will predict that particular class. So that's the way how the default probabilities will go. But of course, you can keep your own thresholds and you can do it that way. Now, this was the confusion matrix. And as I told you, this was a new learning, especially for this exercise. We can see the confusion matrix, how it looks like. And very clearly, the confusion matrix tells you, it gives you a comparison between the actuals and the predicteds. Okay, so the confusion matrix will give you the comparison between the actual values and the predicted values, and this is the inference we are able to get. So we are able to see the actual uh, uh, the values, and we are able to see the predicted values. This is how we can understand the confusion matrix overall. Okay, so you can clearly make out the actual values vis-a-vis the predicted values. Okay, that's the inference you can make. So you can see that. Let me write it down. This is setosa, this is versicolor, and this is virginica. Remember, along the columns, we have the predicted values, and along the rows, we have the actual values. This is the order in which the data will be presented once again. And what is the benefit? The benefit is that you can look at these individual numbers and understand how the model is performing. So whatever model you trained on the training data, how is that model performing on the unseen test data? So you can see there are 12 such cases where the model predicted setosa and actually it is a setosa. There are 8 such cases where the model predicted. There are 8 such cases where the model predicted versicolor and actually it is a versicolor. And there are this many cases where the model predicted virginica and actually it's a virginica. There are 9 such cases. So you're able to very clearly understand how the model and how many correct predictions the model is doing. But what is more important is to understand the number of incorrect predictions. You can see. Okay, so now we can also understand the number of incorrect predictions. Okay, so we can make out how many incorrect predictions the model is making, especially the false negatives and the false positive part. So for example, you can see, and here we can see that there are this one incorrect prediction, because the iris one is a very good data set, because we already saw that the classes are very well separated. So there's very few incorrect predictions happening, one of which is this one, where there is one instance where the model predicted virginica. You can see the column total is virginica. So there is one particular instance where the model predicted virginica, but actually it is a versicolor. So that is the inference we are able to make. So there is again one particular instance where the model predicted virginica, but actually it is a versicolor. So that is the inference we are able to make once again here.